Thank you. Dear colleagues, good morning. I'm Shiguang Shan, and I'm the co-program chair for this conference. I will chair the first session on Keynote. The speaker is Professor Shiguang Shan. I have a brief introduction about Shiguang. Shiguang is a professor in Institute of Computing Technology, Chinese Academy of Sciences, and also a professor of the University of Chinese Academy of Sciences. Shiguang research interests including computer vision, pattern recognition, machine learning. Most focuses on face-related research and neurosciences. Today his talk is about gaze and its application. It's an interesting topic related to CV and brain and neurosciences. Shiguang also being used to be and also is area chair for many conferences, major conferences, including ICV, CVPR, Neuroproceedings, and so on, for more than 10 times. And he also being associate editor for many journals. He is also a fellow of IEEE. And right now he's the director of the intelligent information processing of CAS. Shiguang made a lot of publication, and his research not only in CV. Right now he moved his interest in, I think, more on brain and neuroscience. So Shiguang, let's have your talk. I leave the floor to you. Okay.
I have to use the USB.
Yeah. Here.
Yeah. Okay.
Do you have a USB stick?
Yeah. Okay. Yeah. I think it's here. Okay. Thank you, Professor Chen. Actually, we are very familiar because we closely work together for many years. Ladies and gentlemen, good morning. It's my great pleasure to give a talk here in Istanbul on this very my favorite conference, actually, because I work in this area for almost 25 years. I also attended this conference for maybe about 6 to 10 times. I don't remember exactly. Actually, previously I worked on face recognition, actually together with Professor Chen for 20 years. In the past 10 years, we all know that face recognition seems to have been solved. So we have to move to some new topics in this area. So 10 years ago, we tried to move our attention to effective computing based on face images or face video. During this kind of research, we found that gaze is very important clues for effective computing. So we try to do some work on gaze analysis and applications. Actually, there's another word, it's called Oculesics. So I think Oculesics is a little a topic a little wider than gaze estimation. So I will briefly introduce what is Oculesics. Actually, based on Wikipedia, Oculesics is a subcategory of kinesics. it's the study about eye behaviors, especially the study of eye movement, behavior, gaze, and eye-related nonverbal communications. While it has a very rich, contents about Oculesics, including gaze estimation, eye movement, eye behavior, and even pupil responses. Gaze estimation is one of the most important research topics in this area because as the old proverb says, the eyes are the windows to our soul. So it's very important for us to analyze the eye area and understand the emotion or some other intents of our human beings based on the eye area. And it's in our daily life, I think we all know that the eyes are highly related to emotions. For example, if you feel surprised, then generally your eye will be open widely. And based on the action unit's definition, most of the emotions are related to the eyes. In the other direction, the eye behaviors are also mostly with emotional or cultural implications. For example, if I look down, it might mean I'm a little fear about something, but actually it also depends on the culture. For example, in some culture, eye down might means respect, right? So it's culture dependent, but most of the eye behaviors are emotional related. And the eye analysis is also a fine-grained analysis problem. For example, for the eye movement, for example, when we read a book, the scanning pattern of our eyes is also very complicated. At least there are 5 different types of eye movement, including CKs, smooth pursuit, etc. So it's a kind of a very fine-grained recognition problem. Of course, eye behavior analysis has a lot of potential applications, from the assessment of neurodevelopment, gaze attention analysis, human-computer interaction, and also it can be used to surveillance the driver. For example, when the driver tried to turn left, whether he looked at the back mirror, for example, and also it can be used to analyze the market or do market survey. And also we can analyze what the users like to look at during advertise. So there are many other potential applications. For gaze estimation, actually, we can use different devices. For example, as we know, there are some special devices named eye tracker with some extra light to measure the gaze. And also there are some head-mounted eye tracker. But in our research, we try to use general consumer webcam. In this case, actually there are 2 different categories of research topics. The first category is we use the camera to capture the head or the face of the user. And then in the image, there's the face of the person, but there's no the fixation target of the person. For this case, for the other case is that we will capture both the face and the target of the person in the image. So for the first type, it's generally called a 3D gaze direction estimation or gaze estimation. We try to estimate the yaw and the pitch of the gaze direction. Based on the 3D gaze direction, together with the position and the relative geometry of the person and the screen, we can then estimate the 2D fixation point on the screen. For the second category, most of the research focus on 2D gaze following. That is, we try to estimate a heat map about the fixation target in the image. When it moves to 3D, then it's the 3D gaze following. That is to detect the fixation target in 3D space. So after the brief background introduction about the Oculesics or gaze estimation, in the following I will introduce some of the technologies the researchers published in the past several years, including some of our works. The first part is about gaze estimation technologies. That is, we try to track an eye with the face images. That is 3D gaze estimation. So for 3D gaze estimation, of course, we can model this problem as a deep learning problem. Then we can use traditional deep learning-based methods. We collect a lot of data with the ground truth answers in the training set, and then we learn some neural network to predict the 3D gaze. For example, in 2017, in this work, they try to use the face image as the input, but as the most important facial part is the eyes. Therefore, they use the spatial weights to emphasize the face area to estimate the 3D gaze of the input face. In this work, they try to estimate the gaze by combining both the whole face image and the eye image together. They use two different neural networks, and then they combine them together to get the final 3D gaze estimation results. In this work, they try to use small images. That is, they use a video of face images, and then they use LSTM to combine the results of many images, many frames together to get accurate gaze estimation results. Because the data, the data with the annotation is generally limited because it's not that easy to get the ground truth of the gaze, right? So many researchers are now focus on how to explore unlabeled data or weakly labeled data. In this work, they try to use the weak label that is look at each other as the weak supervision to enhance the 3D gaze estimation results. I think I will also mention how we can estimate whether two persons look at each other later in the second part of my report. In this work, they try to use several cameras together. For example, they use two synchronized cameras to estimate the 3D gaze estimation more accurately. As I have said, it's understandable that it's not that easy to collect or to label the 3D gaze of any input face image. So generally, the gaze data with the ground truth annotation is very limited in this area, and most of the data are collected in lab-controlled environment because we have to get the ground truth gaze of the image. Therefore, we have to get the collect the data in lab-controlled environment. Therefore, it's very important to leverage large-scale, unsupervised data to learn the representation of gaze. So this is one of the challenges. The other one is that when we collect data, annotated data in the lab control environment, but in real-world applications, we have to make the algorithms work in real world. So there's a very big or huge domain gap. As Ramachalapa said yesterday many times, domain shift. So how to process or handle the domain adaptation problem is also very important. So first, I think I will introduce one of our work on self-supervised gaze repetition learning, published in 2021 ICCV. So the motivation of this work is that we have only limited gaze annotation. For example, maybe we have only 100 face images with the gaze annotations. So how can we leverage large-scale unlabeled data? And the other challenge is that the gaze feature is coupled or entangled with other factors. So we need to disentangle the gaze feature and the non-gaze feature. If we do some general self-supervised learning directly by using some autoencoder, for example, we can learn feature, but as it's showing in these two figures, you can see that if we do a self-supervised learning based on some general methods, the learned feature will mostly or closely related to the eye or face identity, but not related to the gaze of the eyes. Therefore, we need some special designed self-supervised learning. So how to do self-supervised learning for gaze? In this work, we leverage two types of very simple priors. The first prior is that the intrinsic feature of the same eye in different images should be consistent, or they should be almost the same, because it's the same eye of the same person, although they are in different images. The second prior is that the gaze of the left eye and the right eye in one image should be consistent or similar. Of course, they shouldn't be the same, because in many cases, for example, if we look at an object near our face, then the gaze of the left eye and the right eye is different, but they should be similar. So these two priors can be used for us to design self-supervised loss. So based on these two priors, we propose a cross-encoder methods to self-supervisedly learn the gaze representation by switching the shared feature and reconstruct the input. To make use of the two priors, we need to construct some training data. That is, we need two kinds of image pairs for learning. One pair is the same eye pair. For example, in a face video, the same person keep unchanged. Therefore, the ID feature, the eye feature of the left eye of the person will keep unchanged. So we can get a lot of same eye pairs. In this case, for the same eye pair, we will use a shared encoder, image encoder, or the eye image encoder to disentangle the feature into gaze feature and eye feature. As the eye feature should be the same, therefore we can change or switch the eye feature of the eye frame and the G frame, that is EI and EG, can be switched. And then we use the decoder to reconstruct the input image. If the disentangle is right, then the reconstruction loss should be minimized. The other kind of pair is a sim-gaze pair. That is, as I have mentioned, in the same face image, the gaze of the left and the right eye should be similar. Therefore, similarly, we use shared eye image encoder to disentangle the eye image into eye feature and gaze feature, and then we switch the gaze feature, that is GI and G key, and then we reconstruct the input of the eye image. So using these two kind of loss functions, then we can do self-supervised learning. Here shows some intuitive observations. By using this kind of self-supervised learning, we can get similar eye features for the same eye and similar gaze features for the left eye and the right eye of the same image. It's also very obvious that if we estimate the gaze from the eye region, the result should be similar or should be the same as we use the whole face. Therefore, we further extended the cross-encoder to cross-encoder plus by incorporating the whole face image together to further enhance the self-supervised learning. So we can get more loss functions to work together to do the self-supervised learning. Here you can see we simply also use another encoder to encode the whole face image, and then we get the left eye gaze and the right eye gaze and the face ID feature, and then we can switch the gaze feature or the eye feature to have more loss functions. So we do experiments to validate the proposed ideas. We generally use the data sets, including the Columbia and the UT multiview, and also MPI gaze and face gaze data sets. Please note that we use only 100 labeled samples to learn the supervised part of the gaze estimation. So it's a small scale data set for gaze estimation. As you can see, using our cross-encoder methods, we achieved the best results on all the 4 different data sets. And we also do ablation study to validate each part of our cross-encoder and cross-encoder plus methods by combining the gaze similar prior, the eye consistent prior, and also further introducing the whole face image as the input. We progressively reduce the gaze estimation error. Here shows visualization results. As you can see here, using the self-supervised encoder, the gaze feature of the left and the right eye are similar, and the gaze feature of the different images of the same eye is different, and the intrinsic eye feature of the left eye and the right eye are different, and the intrinsic eye feature of different images of the same eye are very similar in feature. And we also measure the mutual information between the gaze feature and the gaze. As you can see, the mutual information is much better than previously using some general self-supervised learning methods. I I will skip this one. And also we try to visualize the feature clusters, as you can see from these figures. On the training data or the testing data, the intrinsic eye feature are clustered according to basically the identity of the face, and the gaze feature are more scattered. So the second work I want to introduce is a source-free adaptive gaze estimation method by uncertainty reduction. For this work, the goal of the work is we want to meet the challenge that get the main gap between the lab-controlled training data set and the real-world application. So the basic idea is that we want to use some targeted, unlabeled targeted domain data to adapt the trained gaze estimation model based on a supervised source domain. And the basic idea is we found that the solution is, of course, we try to train a source model based on labeled source domain data, and then we want to we don't want to use the training data in the source domain again, but we want to use some unlabeled target domain data to adapt the source trained model and to adapt to the target domain. So for this work, the basic idea is based on some observation is that the relationship between domain gap and model uncertainty. We found that the model uncertainty and the domain gap is highly related. That is, if the model uncertainty is higher, then if the domain gap is higher, then the model's uncertainty is also very high. And if the domain gap is small, then the model uncertainty will also small. Therefore, we try to reduce the domain, the uncertainty of the model or the sample in order to reduce the to reduce the gap between the source and the target. So based on this observation, we try to reduce the cross-domain gaze error by reducing sample and model uncertainty. By the sample uncertainty, we mean that if the images in the target domain is noise, or the noise is different from the source domain, then we want to enhance the quality of the samples in the target domain in order to reduce the sample uncertainty. For model uncertainty, we measure this kind of uncertainty by using the variance of different gaze estimators on the same sample. So here we use several or a series of gaze estimators together to compute the variance to measure the model's uncertainty. How can we get multiple gaze estimators? Actually, we simply use the gaze estimators produced during the training process. That is, we store several models during the iteration of the training process. So the framework of this work is we first will given the source labeled source images, then first we will use a face enhancer network to enhance the quality of the image, and then we build a gaze estimator using some deep neural network. And during the training process, we will store a series of gaze estimators. And in step 2, we will adapt to the target data by variance minimization and pseudo-label supervision. That is given some unlabeled target images. We will fix the face enhancer to enhance its quality, and then we use the series of gaze estimators to compute the variance of the results, and then we compute the average of the multiple gaze estimators to get the pseudo label, and then we do the gradient back propagation to train the model. Then in the third step, finally we will do the inference on target data with the face enhancer and the mean estimator of all the gaze estimators. So we also do a lot of experiments to validate the proposed results. We use two different data sets as the source domain and the other two as the target domain. And we compared with the previous methods. As you can see from this figure, our results achieved the best results. The unregard with a subtraction sign is the method without face enhancement. As you can see, even without the face enhancement component, our result is also very good. And we also do a lot of ablation study to show the different part of our method, how they works, or how they can reduce the error rate of the estimation. Here show some examples how the face enhancer can reduce the error, and also how the gaze estimate, the mean average can enhance the results. So this is the first part of the first part. Okay. Then I will introduce some eye tracking with the scene images. That is, in this kind of face images, we have the face and the target together in the same image. Then we try to estimate where the person is looking at in the image, as shown in this video. So actually, it's the task to estimate the fixation point of a person. For this work, of course, there are a lot of previous works. They try to, for example, in this work, they try to leverage both the gaze mask and the saliency map together to estimate the gaze following results. They use two branches. The first branch is the saliency pathway, and the other one is the gaze pathway. Then they combine them together to get the final results. In this work, they try to make use of depth information. Of course, they don't have the depth as the input, but they try to first estimate the depth of the input image, and then they can get some 3D clues to combine together with the gaze estimation results to get better results. In this work, they try to use the object detection to further enhance the fixation target estimation. While in this work, they try to leverage both the depth information and the gaze direction together to enhance the 3D gaze following results. So in this direction, we recently also do a work on 3D gaze following and the multi-view scenario, because for gaze following, especially for 3D gaze following, actually it's very important for us to get the 3D more 3D clues to achieve the more accurate gaze estimation results. If we have only single view, then there are many very challenging problems, including occlusion, or both of the eyes might be occluded, or the gaze target might be occluded. So we want to make some difference. That is, first we try to construct a multi-view data set. Then we can solve these kind of problems. The advantage, of course, is it can help us to understand the 3D seeing, and also we can provide occluded facial information. As you can see from this figure, these images, the green point is the true gaze target of the individual in the blue box, and the yellow one is the detected gaze target from multi-view, and the red one is the target detected from a single view. We also proposed a method to combine on the multi-view gaze target results by using a semi-automatic data annotation process. We almost automatically not fully automatic, but semi-automatically annotate the collected data. First, we do head detection, and then we match the heads of the same identity across different views, and then we manually annotating the 2D gaze targets across two different views, and then automatically annotating the remaining views automatically. In this data set, we have 4 different views, and we collected the data from 33 different people, and we have about 400 different videos, and we also have 2 different depth videos. The total frames is more than 209,000 frames in the data sets. We have totally different 13 camera poses. So it's of course, although the people in the person in the data, the number of the number of person in the data set is not that large, but the data set is in terms it's large in terms of frames of videos. We also proposed a method try to sharing the information between the multi-views by learning the relationship between multi-views using self-attention. That is, we firstly use a single view feature extraction for different views separately, and then we can get tokens from multiple view, and then we concatenate the tokens together by using self-attention layers to integrate the results of multi-view, and then do the gaze target prediction. Here, this table shows the results of our methods. As you can see, our results is it's better than the best previous methods, but not that bad, not that good. But I think this is a very preliminary study. Not it haven't make full use of the multi-view information. In this case, especially for large pose images, the gain from the multi-view is especially impressive. So this the first part of my talk, and then I want to introduce some works on eye behavior analysis. The first part is gaze attention analysis, especially for ASD children. As we know, it's a big problem for ASD children, and in the neuroscience study, it's also obvious that the gaze attention of the ASD children is different from typically developed children, including the face processing pattern and for example, the ASD children prefer non-social signals, and they also prefer repeated moving objects. Based on these observations, we want to use gaze attention analysis to help to estimate, to access the ASD. Our basic idea is that whether we can ask a children to watch some TV or some, for example, cartoon movie during the children watching the movie, we analyze his or her gaze attention, and then we might have to diagnose the ASD. Of course, the basic idea is that we want to find the difference between the gaze attention of typically developed children and ASD children. Of course, we can use some well-developed devices, for example, some eye tracker, but we know these kind of devices are very expensive. Therefore, it's almost not possible to install widely in, for example, countryside area. Therefore, we want to study whether it's possible that we can use some only consumer level web camera to capture the gaze of the children. So we do some work to estimate the point of gaze on the screen. Based on the methods we developed and I introduced previously, we first estimate the 3D gaze of the children, and then we do some simple calibration. That is, we ask the user or the children to look at only 9 points in on the screen, and then we adapt that model to this person and this screen to estimate the gaze, the fixation point on the screen. Here the video shows the results. The black spot is what is where we ask the person to look at the screen, and the red circle is what we detected or estimated from the face images input from the web camera. Actually, we also adapted this algorithm to a mobile phone, and we cooperate with Oppo, and the results is also pretty good. As I have said, we want the children to look at a short video. For example, we selected one of the Tom and Jerry video. We asked the children to watch the video. For the left video, it's the fixation heat map of typically developed children. The right is the ASD. So you can see this ASD children is especially interested in the cars on the corner, but the typically developed children will try to predict where Jerry has gone, right? And this is another example. We found that the ASD children is especially interested in some fixed motion object, but the typically the TD children will focus more on the faces of in the video. We also do some significant difference analysis by using several videos. As we can see from the p-value, it seems that there are significant difference in the gaze preference between ASD and TD children. The other part about eye behavior is when we do social communication, how our gaze behavior will change. Of course, in physiology and cognition research, it has been known that we can measure the gaze direction, looking duration, and gaze following often used to assess the engagement or emotion state of the person. And in the computer vision area, there are also some works on detection of very few unique patterns. For example, mutual attention, that is, look at each other, or joint attention, that is, we share attention looking at the same object. For example, in this work, they try to detect mutual gaze using head pose and also the relative position of the heads together to get to classify whether two persons is looking at each other. And for joint attention or shared attention, of course, it's also very important, especially for ASD assessment. It's a very important clue whether the children is good at social communication, because it's very important for us when we communicate each other. We will, for example, we are all looking at the screen. This is the shared attention, right? So in this work, they try to leverage human gaze direction, target, reason candidate, and temporal interframe constraints to identify whether two persons is sharing the same attention. And in this work, they try to detect multiple patterns, including look at each other and shared attention, using a graph neural network. And in this work, they defined 6 automatic level gaze communication patterns following the previous established terminologies. But we think in these 6 different automatic level gazes, they are actually not exclusive. So in last year, we do work to try to analyze the gaze pattern. Actually, we try to redefine gaze pattern in dyadic communication. We redefined 5 different static gaze patterns in two-person communication, including all possible gaze interaction patterns between a subject and its partner. The first one is share attention, and the second one is look at each other, and the third one is that the subject is looking at his or her partner while the partner looks away. The fourth one is his partner or her partner is looking at the subject, but the subject looks some other place. And the final one is no any gaze interaction. Based on this definition, we construct a data set called the GP static data set. In the data set, we have 370 video clips with more than 84,000 frame level annotations, annotated the 5 different gaze interaction patterns. And also we propose a method to learn from a head image, the whole head position, and also the scene image. That is, we have 2 branches. One branch is to we use neural network to encode the two head area, mainly the face area, and also we use the head position embedding. We combine them together to estimate what kind of which interaction gives the interaction pattern the two person is. We evaluate these results. As you can see, our results can enhance, can improve the results significantly. Also, we tested our method on the previous look at each other data set and the shared attention data set. We also achieved the best results. Based on these technologies, we developed a gaze behavior analysis system. Using this system, we further do experiments to analyze the gaze pattern of preschool children with autism and TD children. As you can see from these four figures, in the 5 defined patterns, 4 static gaze pattern, that is mutual, shared attention, single, miss and void, mutual, single, miss and void, all have p-value smaller than 0.01. For these patterns, it implies that the gaze pattern between TD and ASD children are different. So a very brief summary of our related work. The first 2 work is about eye tracking with face images. We try to learn self-supervised gaze representation based on unlabeled data, and also we try to adapt a source-free gaze estimator. We also do eye tracking with the scene images. Some discussions. I think Oculesics analysis is basically underexplored. We need more technologies to, and we also need to discover more applications and also many new tasks to define and to explore. For example, the eye movement modes. And of course, there are many challenges in this area because especially because we have no sufficient data for training and also testing. So it's even hard to measure the progress of this area. And also, many eye analysis tasks are device dependent, scenario dependent, context dependent, and also individual dependent, and sometimes it's even culture dependent. So in terms of technology, I think in the past, especially early days of this area, geometry-based method is very popular, but in the last several years, data-driven is more popular. But in this area, of course, it's very far from big data. So for future directions, I think, of course, we need to collect more data with annotations, and we also maybe need new sensors to capture more eye details. And also, it's still important to leverage self-supervised learning to make use of the big data in face recognition and expression area. And then we need to develop technologies driven by limited annotation data, but based on face or eye foundation models or the vision and the language models. I think we also need to consider techniques guided by the 3D geometry because actually gaze estimation is essentially also a very geometry problem, right? So we also need, I think it's very, very important for us to develop techniques using context, even culture background, because if there's no context, there will many ambiguities in the input image or video. And I think it's for system development, it's also very important to do person adaptive and device adaptive. So with this, I will end my talk. And these works are joint works with Xilin Chen, Jia Bei, Qiaoyun, Yun Jia, Xin Changfei, and Xu Ran. That's all. Thank you for your attention.
Okay. We have several questions. Okay.
Thank you. Thank you very much for this very insightful and enjoyable work. And I actually would like to thank on behalf of my team, because you have mentioned one of our work in ICCB 2023. My student right now is very motivated to continue working on GAZE research. Thank you.
Thank you.
I have two questions. So one question is regarding privacy-preserving GAZE target detection. So can you spend some words on it? The second question is, how do you find existing GAZE target detection data sets? So how can we improve them? For example, the GAZE follow-up data set or the video target detection data sets?
I got the second question is about how to further improve the GAZE attention.
Yes.
Yes, I think for GAZE attention, of course, I think we need more data, of course, but we human beings, I think sometimes we are trying to make use of multiple clues, not only the information in the input image, therefore how to leverage the background knowledge, not in the input, is important. Maybe that's why the big model is now very popular to support this kind of works. So I think it's one of my suggestions, maybe. Okay. Can you repeat your
first question? Sorry. Is about privacy-preserving GAZE target detection.
So the price?
Privacy-preserving.
Privacy?
Yes, because basically we are dealing with the head crops, right? Mm-hmm. When dealing with GAZE target detection, GAZE following. Mm-hmm. So I wonder which kind of approach we can simply follow to make it privacy-preserving.
Can you repeat the last sentence?
So which kind of approach, more or less, we can follow to make it privacy-preserving? So I don't want to essentially process the images, the facial images as it is, but just some insights about it, nothing.
Yeah, actually during, I think privacy problem is of course very important during this kind of research. That's why actually I only introduced some. Actually, our team tried to do ASD research for 3 years, but so far we only collected about not more than 50 ASD data. That's especially it's due to the privacy problem, because we have to get the agreement from the parents of the children, and they generally don't understand what we are doing, because therefore especially in China, they are very sensitive to this kind of research. Therefore, we have to persuade their parents in order to support our research. I think maybe we have to we have to depends on the time, then we can collect more data, at the same time protect the privacy of the children. Okay.
Thank you.
Thank you.
Thank you for your talk. My question also is related with data, is general to all your works. In all the data set that you use you have thousands of images, but only 15 or 40 subjects. How do you know that your model presents generalization capabilities, or maybe learn only the subject because the number of subjects is small in comparison with the 1,000 of frames for each subject?
Yeah, I think we actually don't train we separate strictly the training data, training subject and the testing subject. That is, the testing subject is not included in the training set.
But in your case, for instance, you mentioned one data set with 400,000 images with 50 subjects. These 15 subjects included the test set? May I ask you again? Or I don't know if you understand. In your data set, for instance, in one of them...
Which one?
If you back in one of your data set table...
This one or the
collected... You have one table with the data set. You have one data set with 400,000 images.
33 people, right?
One of them.
This one, right? Do you need this one?
Maybe this one may help. Okay. You have here, you have nearby 300,000 frames, but only 33 subjects.
Yeah.
How do you know that you can reach generalization capabilities, or maybe the model only learn these people?
Yeah, I think it's of course very important to have a data set with more person in the data set. But actually it's very complex to collect this kind of data. So currently we have only 33 people in the data set. We are still trying to increase the number of the person in the data set. And we also want to we also want to collect some data from the internet, not exactly the same scenario, but maybe we can leverage that kind of data to learn the model.
Okay, thank you.
Thank you.
Okay, yeah. So my question is, what's your opinion on new sensor technology, right? So active sensor, active with active illumination, and also probably even the camera will. This kind of neurosensor technology make this problem easier.
Yeah, it's a very good direction. That is, we don't use the common web camera, for example, near infrared or some other sensors, including depth, for example, RGBD camera. Actually, in this data set, we also collected RGBD and also near infrared images. And we are not hardware experts, therefore we haven't designed more special devices currently, but it's really a good direction to go in the future.
Yeah, this company SMI, right, was bought by Apple, right? Supposedly, I was wondering, is there any sort of new data set or new product available from them, right? I think they are for head-mount device.
Yeah.
Anyway, the second question is how do you enable ground truth for all your gaze kind of work, right? When you collect a data set.
Recording in progress.
How do you establish ground truth?
The ground truth for this one? Yeah. Actually, I have introduced how we annotate, we semi-automatically annotate the data. For the second step, it's fully automatically. For the third step, we manually annotating the 2D gaze targets across two views. That is, in the image, we annotate where the person is looking at. We annotate the 2D gaze target in two different views, and the other two views are almost fully automatically annotated.
Thanks, Professor.
Hi, very nice talk. Thank you. I think you're working on an important topic. Gaze is so critical to social communication. I was wondering about the manual annotation. Some of your work depends on manually annotated gaze. So one question would be, what is the level of agreement that is possible between annotators, and are there any kind of hardware-based ground truth to compare to the inner observer, inner coder reliability? Because so much of what you do depends on the accuracy of the ground truth. And so I'd like to know a bit about how do you assess that, and how well can you do?
I think this is a very good question in this area. I think, as I have introduced, there are some previous work. They try to use some devices to automatically and accurately get the annotation, but it's very complicated and it only works in the lab environment. For human annotation, I think what we can do maybe is that we use some crowdsourcing methods. That is, we ask several persons to annotate the same image or same video several times, and then we get some average, and we remove some annotations with a very large disagreement. Even by using this kind of methods, we can't guarantee the results is correct.
What would be ICC for ground truth?
We actually don't do this kind of experiments.
I think maybe in two aspects. Okay, one is we have a setting when collect data, such as we have synchronized collect data. You have some points here, here, and there. So because you sit here and the direction is fixed when you collect data. Another case is when we have interaction. We have see somewhere, and this is manually, that's in subjective. And for the data collected, for the ground truth, it's objective. So we have some spatial targets. That's okay. You see these points, and we know the direction exactly. We have the ground truth. We have a collection room. Yeah.
So how well can?
Like in CMU. Okay, we collected the pi. Okay, we have different cameras. We also have different directions, like the camera. Yeah. In that case, we have the ground truth. Okay. Yeah.
Okay. Thank you for the.
Sir, thanks for the nice talk. I have a question regarding the disentanglement part that you introduced for ICCV work. So,
Why you?
So I was thinking whether the gaze features are themselves entangled with different forms of features, such as emotion, let's say, or health, let's say. So achieving a naturalistic representation out of it for particular gaze, I find like do you think that separating the eye features and gaze features, is it sufficient enough?
I think you are talking about the first work I introduced.
The IEEE 2024.
The disentangling.
Yeah.
Yes. That's why we try to separate the gaze feature and the non-gaze feature.
Yes.
All the other features are included in the non-gaze feature, or that is, we call it eye feature.
Yes.
That's why we use the reconstruction loss.
Okay.
Right. So that's I think maybe I'm not sure whether I have answered your question.
Okay. So I was thinking whether is that non-gaze features sufficient enough to capture all the other features, because there could be many other features. For example, there could be health-related features, there could be emotion-related features.
Yeah.
That could also be encoded into these gaze. That might be coming into that might be leaking into these gaze as well. So
yeah,
absolute gaze features, is it?
No, I think yes. You're asking a very good question. Actually, we also rethinking about this disentangling. Indeed, we try to validate whether the gaze feature is only related to gaze. At least so far, we find it's good enough. But in theory, it's really not. It's not guaranteed, right? So maybe we need to add some more constraints to make it more or only gaze related. Thank you.
I have a comment. One of the participants asked regarding privacy preserving. So if you allow me, I can make this comment. I just want to make a comment regarding one of the questions asked related to privacy preserving. So if you allow me, I can make the comment. Can I?
Sure.
Okay, thank you. Just to let you know, there is a technique or technology which is called homomorphic encryption. So if you use homomorphic encryption, you can directly use the encrypted data to do the processing. For example, if you want to train a neural network or you want to do any other operation, you can use homomorphic encryption. So this is very different from conventional encryption, in which if you want to do an operation, you have to decrypt the data. And if you decrypt the data, then definitely the data is prone to all sort of attacks. So this technology solves this problem. So all you have to do is encrypt the data using homomorphic techniques, and then the processing can be done in the encrypted domain. Thank you.
Okay. I think you make a comment, right? Thank you.
Hello. Okay, we can have only the last question because we a little bit delayed. Yeah. And I think Shiguang will be here for several days. So yeah. Okay, so last question.
Thanks very much. Excellent talk.
Thank you.
I was really interested when you mentioned 3D geometry and personalization of gaze, and kind of I was wondering what aspects of gaze are personal. So, you know, essentially our systems learn to understand gaze from a kind of average perspective because we have lots of different people in the training. But if you're learning from a particular person, what kinds of things can you learn about a particular person's gaze?
Yeah, I think for the system, if we have a large-scale data set, the number of the person in the data set is also very large, then maybe adaptation is not that difficult. But especially if we have a small number of persons in the data set, then maybe, for example, the distance between the eyes and and the shape of the head is different for different person. Therefore, maybe it's good for us to do some adaptation. According to our system development appearance, and if we ask the person to look at 9 different screen points, then the system performance will be improved a lot. Yeah. Okay. Thank you.
Okay.
Thank you.
A gift for you.